Today we're going to take a look at uncertain digits, significant figures, and scientific notation. Whenever I make a measurement, I rate that measurement to a certain number of digits, and we say that that number of digits is the number of significant digits. The last digit that we write, I like to call that the uncertain digit. So let's say I make a measurement here. I'm going to place this 0 at the end of this red line and measure its length. Then the first digit here, the 1, 2, 3, 4, well, that's obviously a 4. There's no uncertainty there. And then I've also got these grid lines here, and I can see that the red line shoots a little past the 3 here. So I'm also certain about that second digit. Generally, you can go a little bit farther. So I might estimate my next digit here to be a 2. It seems to be about 20% of the way between here and here. But I'm not sure of that digit. It might be a 3, it might be a 1. Even if I put a whole bunch of grid lines in here, it wouldn't really help much. Unless perhaps I had a microscope so I could blow everything up and really see where the edge of the line is. So this last digit that we write has some uncertainty. And we don't want to write any digits beyond that, because if we're uncertain on this digit, then we really have absolutely no idea about the next digit. So how would you write the measurement below? Pause the video, try the question, come back for the answer. Well, we'd start with that 11 centimeters. We're beyond that. We're also beyond 5. We're beyond 6, but short of 7. So the next digit's going to be a 6. And then we can estimate kind of where we are. Seem to be about 40% of the way between the two grids. So I'd write that down as a 4 centimeters. So we could write this answer to 4 significant digits. So how many digits we write down really depends on the grid lines, the scale lines on our measuring device. What I'd like you to do here is, for each of these measurements done with a different meter stick, write down your measurement to an appropriate number of significant digits. So pause the video, try the question, come back for the answer. In the first case, well, we're already kind of uncertain on the first digit. We're not sure how far across 100 centimeters this is, but I'd say it's about 20%. So that 2 would be significant. Now our answer is certainly not 2 centimeters. We need a 0 in there as a placeholder. So this would be 20 centimeters, and only the 2 would be significant. In the second example, definitely a 2, but then we've got to estimate our uncertain digit there, and I'd say it was about a 2, so we'd have 22 centimeters. 2 significant digits this time. In the third example here, we're certain on the first 2, we're certain on the second 2, and then we've got to estimate between the grid lines on the third digit. I'd say that was a 5, so we'd end up with 3 significant digits, 22.5 centimeters. So when we write down a measurement, let's say 5.28 centimeters, then we just need to count up those digits, 1, 2, 3, and that would be the number of significant digits. So this would be 3 significant digits. So generally any digit is significant, but there is one exception, and we kind of saw that already. So all digits are significant except for zeros that only act as placeholders. So we saw in that example with the ruler that I wrote an answer down, a measurement down of 20 centimeters. But only the 2 was significant. And I had to put the 0 in there to say the number was 20 and not 2. But really what I was saying is that the length was somewhere between 15 and 25 centimeters. So this here would only be 1 significant digit. Now these significant figures become really important when we start switching units. If we make a measurement, let's say I say it's about 1 kilometer to the school. I make a statement like that. It's based on a measurement. Then if I were to switch units, I would say go to meters and I'd have 1,000 meters. Well, this number's got 1 digit in it, this one's got 4 digits in it. How is it that I got a whole bunch more precise just by switching units? That can't happen. These zeros here are placeholder zeros, and they don't count towards significant digits. So when we switch units, we can't change the number of significant digits. Both of these numbers are 1 sig fig. Or similarly, if I said the width of your finger is about 1 centimeter, so I've got a measurement to 1 significant digit. If I switch units, that would be 0.01 meters. These should both be 1 significant digit. This 0 here doesn't count as a significant digit. It's just there as a placeholder. We want to say that it's 1/100th of a meter, not 1/10th of a meter. So likewise, both of these are 1 significant digit. Now we have some conventions that we use so that readers can tell whether or not a 0 is significant or not. If we want to write the number 200 to 1 significant digit, then we just put the zeros in there and we don't put a decimal place. If we want to say that we really know this digit, it is significant, but this other 0 is just solely a placeholder, then we usually underline or put a dot above the 0 that we want to say is significant. So this would be 2 significant figures. If we put the decimal place in, then we're saying we really do know those 2 zeros. Those are both significant. That would be 3 significant figures. And then of course any zeros that we write after the decimal place are going to be significant. We wouldn't write that 0 at all unless we knew it was really a 0. So this would be 4 significant figures, and this here would be 5 significant figures. So the conventions to watch for is if you write the decimal in, you're saying the zeros are significant. If you want to denote a 0 beside another 0 to say it's significant and the other one's not, then you need an underline, or you could put a dot above the 0. Later we're going to talk about scientific notation, and that'll give you a more consistent way of doing it. So let's get a little bit of practice counting up the number of significant digits. And remember, you're really only looking at zeros, and it's just zeros that only act as placeholders that are not significant. Any other number is significant. So pause the video, try these questions, come back for the answer. So in this first one, we're really just kind of observing the notation here. If we underline, then we're saying that 0 is significant. If we don't underline, that 0 is not significant. So neither one of these are significant, and only the 1 is significant. So we've got 1 significant figure. And what's kind of key to remember here is that when we write 100 like that, we're just saying that our number is somewhere between, well, it's got to be bigger or equal to 50 and less than 150. Because any of the numbers in that range, if you round them to the nearest 100, you're going to get an answer of 100. If I round 144 to 100, if I round 144 to the nearest 100, I get 100. If I round 62 to the nearest 100, I get 100. Second example, this time we're saying that this digit, because of the underline, it is significant. So that's a significant 0. The other one is not. This would be 2 significant figures, and we're really just saying that that's some number that is between 95 and 105. It's got to be less than 105, so that if you round it to the tens digit here, you're going to get 100. Now when we write the decimal here, we're saying that both of those zeros are significant. Instead of underlining them, we just put a decimal there, that means they're both significant. We really know those are zeros. They're not merely placeholders. So this would be 3 significant figures, and that represents a number between 99.5 and 100.5. So all the numbers in that range, rounded to the units digit, would give 100. Next one, that's a leading zero. We don't even have to write that zero, so it's definitely not significant. Any leading zeros are not significant. These two here are simply placeholders. We need those zeros to say it's 0.0045, a very small number, and 0.45, which is a big number. So it's only the 4 and the 5 that are significant. So that would be 2 significant figures. Zeros between any other numbers are always significant. Right? If we know that this here is a 4, then we have to know that these 2 digits here, which are bigger digits, we must know them. If we know a smaller digit, we must know the bigger digit. So all of those numbers there would be significant. That would be 5 significant figures. And this last one, well, those 2 zeros are between other numbers. They're significant. And this last zero, well, we wouldn't write that zero unless we knew what it was. It's not a placeholder. If we get rid of it, it doesn't change the number. So in other words, all of those numbers are significant. That would be 6 significant figures. And a little warning here, this is something that sometimes comes up. Exact numbers have an infinite number of significant digits. So for instance, in math class, you might have heard of the number pi, and it's 3.1415, and the digits just keep going and going on indefinitely. But another example of an exact number would be 31. So for instance, there's 31 students in the class. There's exactly 31 students in the class. There's not 31.3 students in the class. And if I want to calculate an average, I need to divide by 31. But that 31 isn't just 2 significant digits, it's really 31.0000 indefinitely. That's an exact number with an infinite number of significant digits. So we want to make that distinction between measurements, which are going to have a finite number of significant digits, and exact numbers that have an infinite number of significant digits. I don't like to give a lot of rules for significant figures, because I think if you understand the idea of a placeholder zero versus a zero that's really a zero, then it's not a problem. But if I were to give a few rules, this is what they'd be. So first of all, if you've got zeros between other numbers, so I've got a 2 and a 3, and then I've got some zeros in between, and then another number, then all of those would be significant. Or if they're in front of the decimal and behind a number, so if I've got something like 2, 0, 0, 0, and then I write that decimal place, these zeros in front of the decimal place would be significant. If they are at the end of a number after the decimal place, so if I have a number like that, and then I start writing some more zeros, I'm only writing those zeros because I know they're really zeros. They're certainly not placeholders, because if I drop a zero out, it doesn't change the number by a factor of 10. So these here would be significant. Those ones in front and this one here would not. Or when we use that underlining or dot above notation. So if I saw something like 200 and I underlined that zero, I'd be saying that zero is significant, but this one's not significant. Another example, pause the video, write down the number of significant digits for each of these examples, and then come back to the answer. First one has 5 significant digits. They're all significant. These zeros between numbers, so they're all significant. Only the 7 is significant here. The others are placeholders. All of these are significant. These 2 are placeholders, so that would be 3. All of these are significant. All of these are significant. All of these are significant. These 2 zeros are not beside the decimal place.
All of these are significant. These zeros are beside the decimal place, but clearly every time we write down another zero here, we're saying we know more detail about the number. That's an extra significant digit. 3 significant digits here. These are placeholders, these first 3, so that's only 1 significant digit. These are all significant.
Scientists tend to be a little bit lazy, and we really don't like writing down numbers like this one here. Turns out this number here is the charge of an electron, and the way that scientists would write it is 1.6 times 10 to the minus 19 coulombs. This here notation is called the scientific notation. And it certainly takes a lot less time to write it this way, but there's another advantage as well, and that's related to significant figures. You see this number here, it's called the mantissa. But it's always some number that's greater than or equal to 1, and it's got to be less than 10. And because it's always a number between 1 and 10, every single digit in the mantissa is significant. So every digit in mantissa is significant. So you don't have to do any of this messing around with these placeholder zeros to determine whether we should count them or not. We just count up all the digits in the mantissa, and that's the number of significant figures.
So let's take a look at how we write these numbers in scientific notation. Let's take a first example of 101,000. We want to write that in scientific notation. Now, if we want to get a number between 1 and 10, we'd have to take the decimal place, which is here, and we'd have to shift it 1, 2, 3, 4, 5 places to put it here, so that we would get the number 1.01000. Now, we don't have to worry about these 3 zeros because those are all placeholders. So our number between 1 and 10 is 1.01 times 10 to the power 5, because we had to move the decimal place 5 places to the left. And let's try a second example, 0.0002350. So our decimal place is here. We would have to shift it to right here, so we'd get 2.350. That would be a number between 1 and 10. So we're going to shift it 1, 2, 3, 4 places. This time to the right. These 3 zeros are placeholders, so they won't be involved in our mantissa. Our mantissa is just going to be 2.350. All of those numbers are significant. And it'd be times 10, and because we moved 4 places, this time to the right, we get a minus 4 in the exponent. So the steps that we were executing there, we counted how many places the decimal place needs to be moved to produce a mantissa where that mantissa is between 1 and 10. You then write down whatever that mantissa is, excluding placeholders, and multiply it by 10 to the number of places shifted. If that shift was to the left, then it's a positive exponent. If that shift is to the right, then it is a negative exponent. Okay, let's get some practice. Pause the video, convert these numbers to scientific notation, and then come back for the answers. First one, we'd have to shift 1, 2, 3, 4 places, so this would be 3 times 10 to the 4th. This one here, we wouldn't have to shift it at all, so that would be 3 times 10 to the 0. Here we'd have to shift by one place, so this would be 3 times 10 to the first. This one, the 0 is significant, so this would be 3.0 times 10 to the first. Here we'd have to shift it one place to the right to get a number between 1 and 10, the number 3. So this would be 3 times 10 to the minus 1. Here we'd have to shift two places, and we'd have two significant digits, so this would be 3.0 times 10 to the minus 2. And this one here, we'd have to shift 1, 2, 3, 4, 5 places to get a number between 1 and 10. These two digits are significant, so this is 3.00 times 10 to the minus 5. Now some of you might be asking, if I do some measurements and I do the right number of significant digits, and then I do some calculations with those measurements, how many digits should I keep when I write down my answer? And we have two very simple rules for calculations. One rule is for when you're doing multiplication or division. The other rule is when you're doing addition or subtraction. The two rules parallel one another, except in one, you're looking at the number of significant digits. You focus on the number of significant digits in the measurements. Whereas in the other rule for addition and subtraction, you focus on the number of decimal places in the measurements. So our rule for multiplication and division is to keep the same number of significant digits as the entry with the fewest. So for instance, if I were to multiply 2.0 times 3, then this entry has two significant digits. This entry only has one significant digit, so the entry with the fewest number of significant digits is the 3. And I should only keep one significant digit in my answer. So my final answer is going to be 6 and not 6.0. Our addition and subtraction rule exactly parallels this. The only thing I'm going to do is replace the words significant digits by decimal places. So I'd keep the same number of decimal places, dp, as the entry with the fewest. So if I were to take 201 and add that to 1.03, then 201 has 0 decimal places. This has 2 decimal places. Therefore, I want to keep 0 decimal places in my answer. And my final answer would be 202 and not 202.03. So let's try a few examples of this. Pause the video, try the question, come back to the answer. So this one's multiplication or division. This entry has the fewest number of significant digits, that's 2. So we want an answer with 2 significant digits. So we can eliminate these two. When we just multiply those numbers together on a calculator, we get this entry here. So we really want to round that to 2 significant digits. So the correct answer here would be B with correct rounding.
Okay, one more example, a little bit of a trick to this one. Pause the video, try the question, come back for the answer. Now, of course, to calculate an average, we've got to add the 4 numbers. So we had 99.997 plus 100.008 plus 100.011 plus 100.005, and then you have to divide that by the number of numbers, which is 4. Now, you might be kind of confused here by this number 4. You might think it's only one significant digit, but this number 4 is an exact number. There are exactly 4 entries here. There's not 4.1 entries, 4.2 entries. There's exactly 4 entries there. So this really has an infinite number of significant digits. And because of that, we don't want to round our answer to one significant figure at the end. What we're really doing here is adding these 4 numbers. They've each got 3 decimal places. So in our answer, we want to keep 3 decimal places. Because this is an exact number, it won't have any effect on the number of significant digits. So the correct answer here is this one, C, because it's got 3 decimal places. Okay, let's try a similar example, but this time we don't have any exact numbers. Pause the video, try the question, come back for the answer. When we do a question like this, we have to obey the order of operations. So we don't usually write it, but there's a bracket around these numbers at the top. So we're adding those numbers at the top. We want to look at the number of decimal places, and there's 0 decimal places in these 2 entries. So we want to express our answer for the numerator to 0 decimal places, which would give us 72. And we want to do the same thing on the bottom. Both of these numbers are 1 decimal place, so we'd get 27.8. Now we're doing division. That means we want to look at the number of significant digits. The top has 2 significant digits, and the bottom has 3 significant digits. So we want to end up keeping 2 significant digits. 72 divided by 27.8 is equal to 2.5899, and we want to round that to 2 significant digits, so our final answer there would be 2.6. And we wouldn't write those numbers there because they're not significant. So let's summarize the big ideas from the video. The first thing that we looked at was the idea of an uncertain digit, and that was the final digit that you would write in a measurement. We then went on and looked at significant digits or significant figures, and the idea here was to count all digits that are not acting only as placeholders. And then we looked at scientific notation, in which we would express a number as x times 10 to some power. X would have to be some number that was greater than or equal to 1 and less than 10. And by doing that, that meant that every single digit expressed in the mantissa had to be significant. We didn't have to think about placeholder zeros anymore. And then we finished off by looking at how many significant digits do you write in calculations. And it really came down to considering the entry with the fewest number of decimal places, if you were adding or subtracting, and the fewest number of sig figs if you were multiplying or dividing. And we had to be careful because exact numbers really have an infinite number of significant digits. And if we had compound calculations with additions, subtractions, multiplications, and divisions, etc., then we needed to follow our order of operations, always keeping the correct number of significant figures or decimals along the way.
And that's all for today, folks. Thank you very much.